Okay, so I'm Sal Rappoccio from the University of Buffalo. I am a member of the CMS collaboration. I was I was told at lunch there's not a ton of experimental stuff that's happening in the slides, so I'll do a tiny bit of experimental stuff also attached to this, but not. I'm assuming. So how many? So just so I know, how many people are sort of first through third year graduate students? Most of you. How many people are third through infinity graduate students? The fewer, and then postdocs, just a handful. Okay, I nailed this. I assumed the correct breakdown. So if this is a little bit low level, I'm sorry, but there are a lot of I think there's a lot of material to cover. So a little bit of boilerplate stuff. If you are a little bit more advanced and you want to look at all the detail, I used to have a giant list of stuff to look at, but now actually this textbook, Looking Inside Jets, is so I just taught a class with this. It's a great textbook. It has all of the information and all the calculations and things that you would need if you want to take a look at this. If you want a kind of a quick overview, toward Jetography by Gavin Salam is the way to go. So with that, without further ado, so I'm sure you've seen what a jet is in the last couple of lectures, but at the end of the day, it's a spray of particles that's produced by the strong interaction, and it ends up looking sort of something like this. So the question is, why does this happen, and why do they look like they're coming, like they're going back to back, and why do they spread out throughout, start spreading out as they progress? Jets are formed because of the asymptotic freedom of QCD. So what ends up happening is you have a very strong interaction at low energies, and then as you increase the energy of the interaction, the coupling goes down. So this is a plot of the strong coupling constant as a function of the energy. This is I'm on CMS, so I usually know where all the CMS plots are. So I will usually pull them because I just know them from memory. So there are plots from Atlas and all these and other places. This one just has a bunch of summaries. So these are a bunch of measurements of alpha strong as a function of Q. So what happens is you're going to produce something up here at the high end that is where the coupling is low, and then as you progress and you radiate, you lose energy, and so the coupling gets higher and higher and higher. And so how does this work? Is that you'll have some, let's say, this is a very, just full disclosure, this is a very naive picture of how things go, and assumes, perturbation theory works, which only does to a certain extent. And jets have a very rich phenomenology, so to understand what's going on. So suppose you have some quark that's just propagating in space. Now it can't propagate for long, right? Because of all the things that you're learning this week. So most of the time it will radiate a gluon, and that radiation will occur at some angle and some momentum fraction. So I'm going to label the momentum fraction of the radiation as Z, and the momentum fraction of the original parton that is going to be propagating as 1 minus E, and then we have an angle theta. So really you're looking at things that are at the two parameters are how far away your radiation is and how much energy it has. Okay, so that's, just bear that in mind. What happens with this radiation is because of the asymptotic freedom, the probability for a radiation of a gluon will increase as Z goes down or as theta goes down. Okay, and so this is kind of the microscopic instantaneous picture of what's happening. And so if you go down and reduce the momentum fraction to 0 or theta to 0, what you get is something that's infinitely likely, which is meaningless. It just means that it's not defined in this order of perturbation theory. You'll just have other particles that are getting flopped around. If you have a gluon emission at theta equals 0 or Z equals 0 or both. So kinematically, what will happen is you'll have a hard process. It will begin to, it could be created from something, maybe it's a Higgs to BB bar or whatever. That process will have a quark. It'll propagate in some direction, and then soft processes will start creating this a bunch of radiation that will happen around this progenitor quark. And this is what ends up looking like a jet. So you have a progenitor quark. I'm just keeping it in the same line just for illustrative purposes. And you have gluons that will just keep radiating and they keep going forward. Okay. So this is basically what happens and why you get jet formation. So what that means is there's a number of energy scales that happen in any given QCD interaction. The first thing that you have is the hard process. So if you look at so this is a graphic I stole from this archive paper. So you have a process that's going to start like as follows. So you have the protons, let's say. And as this is a PDF school, so you have your PDFs that are sitting here in green here. You have your protons, which are basically big pancake-like things, right? So if you have a sphere and you accelerate it close to the speed of light, it squishes into a pancake. So you have these two pancakes that are going to collide, that are bags of gluons and quarks. Those will then have an interaction. So maybe you'll have some interaction that occurs here in red. All sorts of things can happen before and after. The hard process is only one process that's happening. There are soft processes, there are underlying event processes, there's radiation processes. All of these things are happening all the time. But we're not typically interested most of the time, at least in the things that I do, in the extra stuff that's happening outside of the hard interaction. It's not to say it's not interesting. We need to know what it is, and we have to model it and make sure that it's working. But I'm only going to be focusing on what's sort of happening after this formation. So you have the hard process at very high energy. The strong coupling is going to be low or lower than usual. And then you'll have some products that get produced, and those products will then start to radiate, right? That is the jet process, which kind of has sort of a medium energy scale as jets are formed and they sort of start to spread out. And then there's another process that's happening everywhere, which is these soft processes. So underlying events that is collapsing onto each other, and then radiation of more gluons and quarks off of the original gluons and quarks once you're making jets. Eventually, they will then so you're losing energy, and so therefore the coupling is increasing and increasing and increasing and increasing, and then it basically becomes more than one, the coupling constant, right? So in perturbation theory, we use that coupling constant as a small parameter, but then it becomes not small. What does that mean? Does anybody have any idea what happens when your coupling constant goes larger than one? Perturbation theory breaks down, right? It just means there's more particles. It's not magic or mysteries, right? They're just other particles that are happening. You just can't treat you can't treat the field as a single particle interaction. Okay, so it's not like it's not mystery or magic, and there's no dinosaurs that are happening in here as far as we know. But you have some stuff that's happening here that basically means you're not perturbative. Just a bunch of particles are happening, a bunch of interactions are happening. You can't treat it as a particle-to-particle interaction. So we just kind of usually just make a little blob and just cover our eyes and say, look, there's something happening here. And then after all of those quarks and gluons pull some quarks, other quarks out of the sea, they will form hadrons, which we're going to talk about in a little bit. And those hadrons is what actually gets observed. This is why this is all really, really challenging, is because you have to take all of this junk that's happening all over this event and really kind of reconstruct the interesting part, which is this little part in red. So all the rest of this radiation is flying around everywhere, and that's mostly why jet physics is challenging, but also super fun. All right, so again, let's go back to our picture of our free quark. Now it's going up and down instead of left and right. And it's going to have our asymptotic freedom, and it's going to radiate collinearly mostly. And then we have some, gluons that are going to be floating around. Then those quarks will combine with other quarks from the quantum vacuum. Okay, so you can't have a free quark, and eventually the quark will lose enough energy, and it'll just pop something out of the vacuum. It'll combine something that has the opposite color, or it'll form color neutral particles like pions and kaons. So so we call this fragment that will then fragment into observable particles. So we have pions, kaons, and protons and stuff like that. And what the challenge is now, like I was just saying, what you really have is not you don't have the original quark, right? That's even an ill-defined concept. If I had enough time, I would talk about this, but I I may get some time tomorrow to talk about quarks and gluons, how this actually works in practice, but I probably won't, but I will try. But you can ask me about it if you have questions. So what we really have is this group of particles. It's basically just a group of 4 vectors with the particle ID attached to them sometimes. And then what we need to do is use sort of something like a data science algorithm. We used to just call these algorithms back in the, nowadays they just say, machine learning is just statistics on a Mac. So it's not that different. So we have data science algorithms. We've had data science algorithms way before they were called data science algorithms. We're going back decades. So that's how it goes. So what we really have now is a clustering problem, which is a data science problem, right? So this is something that a lot of different fields face. And so what you're trying to do is grouping n things into k objects. And in our case, it's grouping n particles into k jets. So we have, let's say, 300 particles. You want to group them into 2 jets or 1 jet, let's say. However, there's a very intrinsic ambiguity. You don't know which particle will belong to which jet. And so you have to, we don't detect jets, right? We detect particles in our detectors. And so that we need a jet, some kind of algorithm that's called a jet algorithm to distinguish them. So there's a lot of talks about jets and jet algorithms. This is now, I would say, let's see, 40, almost 50 years old as a field. A lot of material is there. Gavin Salam is our patron saint these days. So his website is probably the first place you should go to whenever you have a question about jets. If there is a Nobel Prize coming about any of the jet substructure or anything like that, he will be the guy or one of the guys to get it. So he's also an extremely good person to explain things. So I will steal entire slides from him, just like everybody else does. I think he's given this talk at this lecture at CTEQ in the past, or at least Marnell has in several. Yeah. So Gavin's I'm just basically, we're all just echoing what he's been telling people for decades. And he's also a very good communicator, way better than me. So, but if you ever have any questions, go there. You can even ask him. He'll be happy to answer. He's the nicest guy you'll meet. So I'm selecting some slides just from here if you want to grab them and see a little more detail. This was in Sao Paulo in 2015. So what we're trying to do is figure out jets that are going to make sense to experimentalists and theorists at the same time. And so jet finding could be thought of as a form of a projection. So suppose you have two at the leading order level, you have, let's say, 2 quarks that are produced from a gluon interaction. Maybe these are, or let's say Higgs to BB bar or anything. It doesn't matter. You have some leading order partons. You have a quark, an antiquark. And you want to define them as jets. And you just say, okay, there's 2 quarks, 2 quarks, 2 jets. Great. Back to back. And one is on one side of the detector, one's on the other side of the detector. Woo, we nailed it. We're done, right? Maybe not. The problems start arising with when you have radiation, right? So if it was just a single particle, it would be totally easy. And that would be like a muon, right? You have Z to mu to mu mu. You have 2 muons. You don't have to do too much clustering afterwards. It turns out actually you kind of do, because even muons radiate via QED. So there is a muon clustering algorithm. We even have an electron clustering algorithm, but they're very, very, very tiny and very, very, very narrow. So you don't really have to worry about it too much. However, if you do work with rivet, this so-called idea of dressed leptons, dressed leptons are just really, really tiny jets from QED. Okay. Anybody familiar with rivet? Just so I get an idea. One person that's waving their hand vaguely. I'm also kind of vaguely familiar with rivet. So. Okay. So the trick here is that we also need this to be safe from effects that have from QCD. So I told you that if you have a quark, it will radiate a gluon at some point. And so if you have a quark that radiates 1 gluon, you don't want this to magically turn into 3 jets always. Sometimes you do, but sometimes you don't. And so what you need is something that will be resilient to something that's called this. This is called collinear safety. And also you need to have some, it also needs to be resilient to a bunch of different things that are going, gluons that are going to be radiating. And it also should be defined at the shower level, and it also should be defined at the hadron level after you've fragmented. So this gets to be a little bit challenging. You really want this, if you look at this as sort of a Monte Carlo event, you could say like this is a MatGraph event where you have, let's say, Higgs to BB bar. You shower it with, or maybe you knew it at next to leading order and it adds a gluon, or maybe then you pass it to the parton shower with Pythia and then has a bunch of gluons, and then the Pythia will finally hadronize this and make a bunch of hadrons, and that's what actually gets done in your Monte Carlo or in actual real life, right? As experimentalists, I only have access to this. But you want this to be the same projection in all of these stages, right? Leading order, next leading order, with the parton shower, and at the hadron level. So that's where all this tricky stuff was found. But this ultimately becomes ambiguous because you don't really know what's necessarily going to happen. So in this case, like you could imagine that there are two jets here, right? They're pretty obvious. One's on one side, one's on the other. This side is pretty clearly 3 jets, right? Or is it 4? I don't know. Depends on who you're asking. Back in the olden days, when those of us with white in our beards and equivalent were youngsters, we did not have very nice jet algorithms. Okay, so we actually had to have a whole it was probably, I don't know, 15-year strategy called the Snowmass Accord to get a jet definition that made sense. So we kind of needed to agree on that. So the jets needed to be something that was easy to implement for an experimental analysis. So those of us who spend our time doing hardware and not necessarily calculating at NLO QCD integrals would be able to do it and understand what we're doing. And it also has to be simple to implement in a theoretical calculation. So it has to also work at the Pythia level, and it also needs to be defined at leading order and next leading order and all the different orders of perturbation theory. And it also needs to yield a finite cross section at any order of perturbation theory, so you don't have any weird effects. And something that would be ideally yielding a cross section that is somewhat insensitive to hadronization. This was not obvious, and this for a long time. This was kind of a headache and a nightmare, and it really made comparing data to theory extremely challenging. And eventually we came up with some ideas that kind of closed the gap here. I think one of these, Dan, were you mentioning this paper? I think you mentioned one of these papers. Anyway, this is the paper from jets about jets from George and from George Sturman and Stephen Weinberg that started describing how these actually work. So this is even way back in the 70s, back with bell bottoms and stuff. What we're going to be discussing is a bunch of different algorithms. I'm not going to spend a lot of time on the history because those are dark times. We're in better times now. We'll move around. One thing I want to highlight though is that this really is a more generic problem that is done in particle physics, right? So clustering is not just for jets. There's a lot of different clusterings that you can do. What we are typically now interested in is something called a hierarchical clustering. So this does matter for jets and jet substructure because we actually use agglomerative and divisive algorithms both in particle physics. So one, agglomerative means you start with the constituents and you merge until some criteria is met to find a jet candidate or even more generally some cluster candidate. Or you could use a divisive strategy where you start from the top down. You do almost exactly the same, but it's in reverse. You start with the agglomeration, you look into the inside of it to see what's happening. We actually do both of these, and I'll talk about both of them today and tomorrow. You can represent these in a lot of different ways. You can use a tree, which is called a dendrogram, or a Venn diagram, which is a nested cluster diagram. But ideally, what you have is some categorization. In this case, you can P1, P2, P3, and P4 can just be 4 vectors. It can be anything. You just need a metric that will define what they some kind of distance. In this case, they're just 4 vectors, and so we're going to use the Minkowski space metric difference between them. So you cluster two of them, and then they form a pairing, and then you cluster the other one into that, and you have another pairing, and you cluster another one, and then another pairing, and then you have your final candidate. Okay, that's the agglomerative version. The divisive version, you start from the top, and then you split into two, so P1 and P234, and then you split P234 into P23 and P4, and then you split P23 into P2 and P3. Okay. You can also highlight this as a nested cluster diagram. So you can just draw the coupling as it, and this ends up looking kind of like a projection of a jet, which is nice. But either one of these are good ways to think about this. And if you ever have to do math to do this yourself, for instance, I make my students do this by hand at least once in their life when they're in their class. It's not, I usually use nice numbers, so they come out a little, because it is an algorithm, you do have to iterate. You don't want to do this more than like 5 or 6 times for 5 or 6 particles by hand, because otherwise you're going to be doing a lot of paperwork, which I don't enjoy. So now in the past, what we've had is something called the seed algorithm. I'll tell you the benefits of why this is useful is because it is easy and circular. Circles are good for experimentalists. Why? Because the area is pi r squared. And we can just say, we're just going to plop these in and we're going to draw a circle. And then we're going to have those stuff that's inside of that. That's going to be our jets. And we're going to correct them with whatever we need to in order to make our, voltages and currents that we measure into zeros and ones for your, for your theory calculation or for your jet reclustering. So, why do you need them to be sort of uniform is because pileup and underlying event are uniform, right? So jets are highly correlated to themselves. Obviously, there's something, but there's a bunch of, as I showed you in this other picture, there's a lot of junk that's just floating around all over the time, all over the place. They're usually it's uniform in 3 space, so it does or roughly uniform for these underlying events. Or it's really not uniform in 3 space, it's uniform in Minkowski space, but yes. All right, so where was I? So that's what we really wanted, is something that's circular so we can correct for it. However, if you have a seed, the way that a seed works is you take a guess. So if anybody's used k-means clustering before, the way that works is you have a bunch of stuff, you initialize it with a bunch of seeds, and then you iterate and you adjust these so-called centroids until you minimize symmetric, but you have to have some initial seeding. Right? You just randomly plop n jets onto k particles, and that may or may not converge to something nicely. There are all sorts of paradoxical cases that make life miserable, and you have to think of all the corner cases, and they're really annoying, and you don't want to deal with it. So they're also not infrared nor collinear safe. So if I go back to my collinear and infrared safety diagram here, if you have some particle that gets flopped around here, if you just happen to plop a seed onto this extra particle that's just floating around, that's going to be the center of your jet, and it's going to be happy with that, which is not good. You don't want it. You want it to actually figure out what the correct version is here. So for a long time, we tried to use these algorithms that were not super convenient. They also were not. We were not able to compare apples to apples with theory before or after hadronization, and so this made our lives disastrously miserable. And in the early 2000s, we decided to just pull the plug and move to something better. And there are seedless variants of a couple of cone algorithms, but they're very computationally intensive. So what I'm going to talk about instead is something called the KT family. So the KT family is a clustering algorithm that looks at particles pairwise. So you just start wherever you want. So you can start in whatever order. You just start with particles. So you'll have some whenever you have some set of n particles, you consider them pairwise, and you look at 2 values. So you create a metric, which is dij, which is the minimum of the KT of the individual particles, I and j, raised to some power n, and then you multiply that by the angular separation between them squared, divided by some distance parameter r, also squared. And then you calculate something called the beam distance, which is just the KT of each individual particle raised to that same nth power. So what you do is that if the minimum of all of these DIJs, you find the minimum of the DIJs and the DIBs. If the minimum is a DIJ, you merge those two particles and put them together into the dendrogram, and you iterate the procedure. If the minimum is a DIB, you're finished. That's the termination condition, and that is classified as a final jet. And you just keep doing this until it's exhausted. So graphically, what this happens is, suppose you have 4 particles, and I'm going, if I had my dendrogram, again, it looks like this, but I'm just going to do this as I'm just going to have it as like a snapshots in time. So let's say I consider these 2 particles first, and I combine them together, and I form a, where did I go? Particle over here. And then I'm going to combine those 2 to look at another particle that's here. And then I combine these 2 and get my final state particle here. Okay. So this means I'm computing this would be the case where the DIJs are a maximum. And then at the end, there are no other DIJs. There's only the DIB. And so I can merge that into a final jet. So this is a good exercise to go through once in your life to do this. What ends up happening is that you can actually choose a couple of parameters. This value for n can take a couple of different values. You can set it to be whatever you want, but we typically use a couple of different specific numbers. So we use n equals 0, n equals 1, or n equals -1. So before I get into some more details, what this looks like graphically is this. So these are eta are rapidity phi projections. So if you take a detector, it looks like a paper towel roll. You take a cut, you slice the paper towel, or you take a pair of scissors, and then you unroll that paper towel, and it will. You plap it on the table. So now you have an unrolled torus here, and you can see that there's what's happening here is that this is phi, this is rapidity. So for the LHC, it's equivalent. It's you can think of this as polar angle, more or less. And the energies are shown on the z-axis here. So the height of so these are calorimeter plots. So the height of the cell is the energy that cell has in our calorimeter. So after the clustering algorithm, you can do a couple of different versions. If you say n is equal to 1, it's the so-called KT algorithm, which is the original version, and it ends up looking looks like this. Now, the KT algorithm was available for a very long time, and it provides very nice, easily theoretically accessible jets. However, if you look at them, they're not circular, right? They look like blobs, and you're just like, paintball, and you shot paintball at something, and there's just a big splat of stuff. This is for n is equal to 1. This is for n is equal to 0, called the Cambridge-Aachen algorithm. It still has the same problem of KT, where these are kind of spread out and not very well-defined boundaries. However, if you set n is equal to -1, magically, the math comes out that all it wants to do is make a circle. So you take the highest energy thing, you draw a circle around it, and that ends up happens to be almost exactly the same as as the anti-KT algorithm. So the anti-KT algorithm is going to be effectively marrying two different things, which is the theoretical things that we really wanted to be dealing with over here. So something that's nice theory-wise, and we can actually compare the different calculations, but it's also circular, which means it's easy to actually utilize and correct. Okay, so this circular nature is very important. And as a preview for tomorrow, as a note, if you look at these, they look like an image. So if I have some time tomorrow at the end of my lecture, I'll go into some of the machine learning stuff that happens when you're looking at this stuff. I don't know if I'll have time because I only have 2 hours, and it's not going to be too much. So what I think about when I think about these clustering algorithms, these sequential clustering became very popular. The KT algorithm is, if I just set n is equal to 1 in this equation here, and I have, and what it ends up looking like is, I like to say that that is QCD in reverse, okay? So what happens if you think about it going from the top down or whatever, actually in time, not in the algorithm, the quark will be moving around in space. It will radiate a gluon. Now I've done it so that I've drawn it so that the quark actually has a recoil here in space. So there's an angle between them. And then I have a bunch of 1 to 2 splittings, right? 1 to 2, 1 to 2, 1 to 2, over and over and over. And that's actually how, at leading order, what happens in QCD, right? If you just look at this in leading order and perturbation theory, that's what QCD is. You have 1 to 2 splittings. Occasionally, you have 2 to 2 because you can have gluon, 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 but that is not as likely to happen. So this is kind of, to first order, this is kind of what ends up happening. The KT algorithm will sequentially go backwards. So it'll take pairs and try to reconstruct the 1 to 2 splittings by going back from 2 to 1s, merging. Okay, so that's why this is kind of QCD in reverse. At the end of the day, that actually does look. So just showing you these pictures again. If you do this QCD in reverse, it looks like these this splotchy thing where it doesn't really look very circular. But for n is equal to -1, it creates this nice circular pattern, which is really easy to use. And it doesn't make any computational difference. Why we didn't like a lot of these in the past is because they're very computationally intensive. But this one is not computationally intensive. Bless you. But it didn't give circular jets. But if we just change n to from 1 to -1, we get our circular jets that we want to get. Don't forget about this one, which is called the Cambridge-Aachen algorithm. If I set n is equal to 0, this part just goes away. You don't have any kinematic information or PT information or KT information. All you have is the angular information of how separated they are. Like I said, it ends up looking similar to the KT algorithm, but we'll come back to this when we talk about jet substructure pretty soon. All right, before I go on, are there questions on this? Okay, so which one of these is best? Depends on what you want to do. We use all of them at the LHC and other places. The KT algorithm is very sensitive to soft radiation, which means it's great for calculating things in QCD and perturbative QCD. You're not artificially restricting your radiation pattern. It's just guessing where it is by picking out where the actual radiation went. This is actually really good for jet substructure, which we're going to talk about tomorrow. But it's terrible for jet calibration, and it's very sensitive to underlying event and pileup because it has a non-uniform area. So it's harder to correct for these experimentally. The Cambridge-Aachen algorithm is less sensitive to soft radiation and only relies on geometric information. And that actually ends up meaning it's usually the best for jet substructure for reasons I will that are probably a little esoteric. So I may cover them tomorrow if I get time, but probably not. But the KT and Cambridge-Aachen are kind of similar in this. It's still bad for jet calibration, and it's still pretty sensitive to underlying event and pileup. And I'll talk about those in a little while. The anti-KT algorithm, on the other hand, is not sensitive at all to soft radiation. It just picks the highest one that's there and draws a circle around it, more or less. And that's great for jet calibration, and it's easy to correct for other things experimentally. But it's terrible at finding substructure on purpose because that's not what it's supposed to do. So we use a combination of these for different analyses on CMS and Atlas and everywhere else. So again, which one do you want to do? What we usually do is we want to find our jets with the anti-KT algorithm, and that's the most of if you pick up any LHC paper or most of any other papers these days, most of the jets will just be anti-KT jets. If you're using if you want to look at substructure, you take the anti-KT jets and you recluster them with the Cambridge-Aachen algorithm, or KT sometimes, to find the substructure, which is what we'll be talking about a little bit tomorrow. Okay, so I've got about 25 minutes. So I want to go into now some experimental aspects of jets. But are there any questions on the theory altogether? Yes. Yep.
Different for CMS, like you can have different. You could do it differently for CMS and then for.
Yes.
So. differences, and then when we're designing jet those differences matter.
Okay, I'm going to answer the last question first. No, they don't. And that's because we've designed jet algorithms so that they're not very sensitive to that. Then I'll answer the first part of your question. So it looks like, so what ends up happening is this picture here. So this is a picture from Pythia. And so, oops. So Pythia is a part-time shower. So what you end up doing is you have your particle. So if I go back to maybe this picture, actually, let me find this one here. So at leading order, you just have quarks and gluons, right? If you add next to leading order, you add one gluon, every n gets a gluon. But what we're asking about is the parton shower. Parton showers are heuristics. So you can kind of pick whatever you want as long as it makes sense and matches the data. And then you have to tune it to the data. So it's kind of guided. There are some physics principles that are underneath it that are guiding the parton showers, but the way that you tune them is different and can vary across experiments. And you can use different parton showers and different models. There's a bunch of different parton showers. Most of them are some version of Pythia or Herwig. There's also a bunch of other ones. There is Vincia and a bunch of other things that are there, but it doesn't really matter all that much. It's just a parameter. It's a parametric way to do this. Most of the things that we do to choose which one to do are for engineering purposes. Something that's fast, doesn't take a lot of storage space. It doesn't take a lot of computational time. That's the kind of stuff we are. But the parton showers are a separate thing that I will not be discussing today on the details of them. Any other questions? Yes.
What's the sensitivity and choice of the model of the parton shower in the sense that what is the error that you commit? You
do get a substantive error. It depends on the analysis. Some analyses are very insensitive to the parton shower model. Some are extremely sensitive to the parton shower model. And we'll talk about it. I'll show you some of the measurements tomorrow. Typically speaking, jet substructure is very, very sensitive to the shower model, but the 4 vector of the total agglomeration is usually pretty insensitive to the parton shower. So it depends on the analysis. Any other questions? All right, so I was asked to give so I flopped in a bunch of experimental slides because I was told you guys have not seen a bunch of too much experiment yet, so I'm going to talk about it a little bit. So different detectors are going to have different strengths and weaknesses, and you want to have freedom to utilize your weaknesses and emphasize your strengths and downplay your weaknesses, right? And all of the detectors are composed of many, many, many detector sublevels, and lots and lots of engineering goes into this, and physics. So understanding how you put that information together is critical to really fully reconstructing your event. This is just Atlas and CMS. So here is Atlas and here is CMS. Again, I'm on CMS, so I have much more familiarity with that. But the principles are the same. So this is an eighth of the slice of the CMS detector cross section. So the particles are being collided here in the center of this little circle, and the protons are going into the page. So you can have a bunch of different detector layers. You can have a tracker, which is basically a giant silicon-based CCD camera. We have an electromagnetic calorimeter, and so does Atlas. These are basically exactly the same coming inside out. It's just this one is a little more zoomed in, so I'm going to use this one. So we have our tracker. We have an electromagnetic calorimeter. We have a hadronic calorimeter. We have a superconducting solenoid that's inside of our muon detector. Atlas has their muon detector interspersed with their toroid for their muons. But I don't know if you've seen this. Have we seen this week? No? No experimental overview at all? Okay. I could have given that talk, but I'm not going to. But anyway, I will. So basically the moral of the story is that we are trying to take individual particles and identify what they are. And the way that you identify what they are, it's a game of like 20 questions. Okay. So how this works is like you have a bunch of different things. We have our tracking, we have our electromagnetic calorimeter, a hadronic calorimeter, and our muon chamber. And typically speaking, that's the cartoon level of all of our particle detectors. Then we have a bunch of different particles that happen, right? There's photons, there's electrons, there's muons, and then there's all the particles that are inside of jets and missing transverse momentum. Sorry, this is not ET anymore. We used to call this ET back in the olden days. So there are a bunch of different particles that happen in collisions, right? Almost everything is what? Pions. Almost everything is pions. So you have something like 90% of all of the particles is pions. So you have pions that will often decay eventually to muons, but normally that happens outside of our detector volume because they're moving so fast, it doesn't matter. There's also neutral pions, which decay immediately to 2 photons because of the via the electromagnetic interaction, because it's like UU bar, right? So they just flop together, and then you make two photons. The next one up after pions is a kaon, which is like a pion, but that has a strange quark. There's a bunch of different versions of kaons. There's a charged kaons that decays more to pions, and then they can decay to muons again. They also have neutral kaons that can either decay very quickly, and they're called very creatively short kaons, and then long kaons, because we're great at naming things. So we have K shorts and K longs, and they're floating around the detector too. The next most likely one is a proton, which is of course stable. That's what most of us are made of, but there's 3 quarks instead of 2, and so it's not as likely to happen as a pion or a kaon. And then of course we have neutrons, which decay almost very usually eventually to a proton, electron, and a neutrino. But a lot of the times our neutrons are moving fast enough that they can make it into the hadronic calorimeter. We do have then after all of that, we can have hadrons with charm or bottom quarks that will decay, that will be produced. They will actually travel some time. So we'll have a hadron that will decay like a millimeter away or something from the interaction point. We can easily distinguish that at this point. We've been doing that for 45 or almost 50 years. So looking at lifetime information is extremely useful for us. And then we also have photons, which we detect. So the game of 20 questions is really to break down, is it a muon? Is it an electron? Is it a charged hadron like a pion or a kaon? Or a neutral hadron like a neutron or a photon? And so you ask 20 questions. Did it leave anything in the tracking detector? Anything that's neutral will not, right? So neutral particles will not leave anything in the tracking. But a charged particle will. And so if it's an electromagnetic object like an electron or a photon, it will deposit most of its energy in the electromagnetic calorimeter. So those are the 2 easiest ones to start with, let's say. So you have a photon, which is an electromagnetic shower without a track, an electron, which is an electromagnetic shower with a track. Okay, so now we've identified that one versus the other. What if it doesn't leave any it just has a little bit of energy all over the place? That's actually a dead giveaway, which is a muon, because muons are the easiest thing for us to discuss. We love muons. Muons are great. And then you have everything else, which is charged hadrons, neutral hadrons, and photons that are inside of jets. And they will charge hadrons will leave a track, leave a little energy in the ecal, and then deposit their energy mostly in the hcal. A neutral hadron will not leave a track, will leave an ecal deposit, will leave an hcal deposit, and will not get to the muon chambers. And neutrinos, just nothing happens. Someday, maybe Dune will detect them. Who knows? So mathematically, that's what's happening. Sort of numerically, this is kind of what you look like. And so this is the fraction of energy that's carried by the various species that are inside of a jet as a function of their transverse momentum. There are data and Monte Carlo on these plots. So what I'm showing here is the charged hadrons, which are in red, the photons, which are in blue. Then there's neutral hadrons in green, and then leptons, which is this tiny little bit in blue up here. As I mentioned, jets are mostly pions, and you can also even figure out the order, right? There's 3 pions, 2 charged, 1 neutral. And so the charged pions are 2/3 of the jet, and the neutral pions are 1/3 of the jet. And the neutral pions decay instantaneously to photons, which means you get about 1/3 photons. So you don't detect the pi zeros, you detect the photons. And if you add all of that up together, it's almost the whole jet. You get a little bit left of strange quarks, which is floating around here, and then occasionally you get a muon or an electron. Okay, so that's jets. And you may, if you're being astute here, you may ask, what's happening here? Is this real? Does physics really do this? No, no, it's not. It should be flat, but this is a reconstruction effect. It's because as your energy gets increases, you have a curved track that becomes straighter and straighter and straighter. It's harder and harder, and as those, it's harder and harder to distinguish what their momentum is, and also harder and harder to distinguish between you and your partner, which was produced alongside your jet. And so what ends up happening is we actually start misreconstructing a lot of charged particles as neutral particles because we lose their track and they get reconstructed as a single hadronic cell. So this is an experimental aspect that we have to account for. The data are shown in the points, and the Monte Carlo are shown in the histogram. So it's an effect that's more or less well understood, right? This is actually a very old plot from our ATEV collisions. It's actually gotten, the agreement has even gotten better for us on CMS, but okay. All right, questions on this part? Yes.
Why are you seeing the reconstruction effects in the Monte Carlo?
Because it's a real, it really does physically happen. This is not unfolded to correcting for detector effects. This is including the detector effects. This is the observable simulation. So you want to, this is like,
It's not like a raw.
no, this has not been, bless you, this has not been, I've not taken out that effect. We do have, when we do a measurement, we take those things out, right? We want to correct for that at the, to get down to the particle level. But this is not at the particle level. This is at the reconstructed level. Okay. Yep. Any other questions? Okay, moving on. Okay, so keeping track with our 20 questions here. There's a bunch of different things that now you have, everything is not perfect, right? We are experimentalists and we live in the real world. We're experimentalists, we're all physicists, right? So, and we all live in the real world. And so you don't get something for nothing, and there is no free lunch. That's something to get to really hammer home. So there's a lot of trade-offs about what is and what isn't a good measurement. We have, these are all taking place in a giant magnetic field. And so the tracking, as I showed here, the way that you do tracking is the particle will come through these things and leave charge deposits in this. And then you reconstruct the curvature by playing connect the dots. And you try to connect all the dots and you calculate the curvature, and you take the inverse of that. It's the PT with some constants due to the electromagnetic interaction or the magnetic field. And that's how you measure it. However, as the momentum increases, this gets straighter and straighter and straighter. And so you can't reconstruct the momentum very easily. It becomes just very, very straight. So, oops. The tracking detectors have amazing spatial resolution. I mean, we're talking microns. It's incredible. These are majestic devices. There's no other way to put it. They're gorgeous. They look pretty. They're very, very, very precise. They are the most precise extended measurement of anything ever by humans. Okay. Let's not understate the technological advantage here. However, just because of geometry, as they get very, very energetic, they get straighter and straighter, so you lose resolution. So they're amazing at low energy, and they're not great at all at high energy. Okay, so you don't get it, you don't get anything for free. But the good news is that gets compensated by our calorimeters. Now, calorimeters are cells of something. Like you have a box that you're looking at, and your particles are going into your box. You can't tell where in the box it went unless you made it more finer and finer. I'm going to put an asterisk next to that statement for the HLAC era because we will be able to do that in the future, but at great difficulty and great cost. But all we did was made another tracker. Somebody told me when I was in graduate school that tracking detectors were kind of like a cancer. They started in the very center and they're just growing out over and over. And eventually we're just going to have a whole detector made of silicon tracking, but it's ridiculously expensive and extremely power hungry and very, very hard to cable. So, okay. But the good news is the calorimeters are good enough. They have poorer spatial resolution, but it's not terrible. The good news is as the energy increases, your calorimeters get better. which is compensating for the tracking, which is getting worse. So there's a trade-off. At low PT, the tracking usually dominates your resolution, and you get a much better measurement from your tracking detector. At very high energy, you get a much better energy measurement from your caliper. So you have to put all that information together. The LHC experiments do that differently, but it depends on detector choices and the way that actually works, and the algorithms that you pick in order to do that. Okay. So what that means in terms of resolution is that muons are the easiest particle to reconstruct. We love muons. They're great. Anytime you have any analysis that can decay to muons, yay. Higgs discovery, muons and photons. Good job. As we keep getting harder and harder and smaller and smaller and smaller, things become weaker and weaker and weaker and weaker, or trying to, interact with less and less. Muons are still the golden channel for everything. Electrons are the next, which are nice to reconstruct. However, they do lose a lot of energy when they go through any material. And so for us on CMS, we have our tracker is so massive. It has a very large material budget. And so we have a lot of conversions. So almost a third of our electrons convert or do some kind of radiation. So we have to be very careful about how we do this. Over the years, we've figured out how to do this well. So we're not terribly worried about it. Electrons are still pretty easy to deal with. Photons are a little harder than electrons because they don't have any track, so you don't know where they came from. So all you have is the energy. So one of the biggest challenges in the Higgs to gamma analysis that Kieran was telling you about is actually pointing where these photons came from. So you have two photons on the other side of the detector. You're just kind of like eyeballing where they went through, to extrapolate back to the center of the detector, and you don't know which interaction point they came from. And so for a long time, it was messing up all of our algorithms because we looked at the vertex with the highest track count, which works for QCD, does not work for Higgs, right? Because the highest energy event has no tracks because it's decaying to photons. So we would miss that we had to make specific primary vertex algorithms in order to make that happen. Okay, so photons are still good, but they're not as easy as electrons. Jets means that you have to combine everything together. So their resolution is the worst. It's just what it is. And missing transverse momentum is even worse than that because all you're doing is taking the sum of everything else that you calculated in the event, calculating their vectorial sum, putting a minus sign on it and saying, yay, there's Susie. Maybe not. So that's the hardest thing to look at. On CMS, this is just the numbers that I have for CMS. We use something called the particle flow algorithm. So we try to take all the particles, we try to track them through the whole detector and put all the information together in a weighted average so that we can reconstruct the total 4 vector. The resolutions are as follows. So if you look at a tracker, the resolutions are, so the PT resolution is actually linear in PT. So if you look at sigma over PT, so this is the fractional uncertainty on the momentum measurement. It's some constant times the PT. So it's linear in PT there. And it also has a term that's added that's just for multiple scattering. That's about at the percent level. So if it's 100 GeV track, you move this decimal place over. So you get basically 5% added in quadrature with 1%. So it's about a 5%, 0.05% uncertainty. Electromagnetic calorimeters, I need to move that thing, but okay. Ours is about 3% over the square root of the energy, added in quadrature with 12% over a linear version of the energy plus a constant. And our hadronic calorimeter is about 110% over square root of the energy, in quadrature with 9%. So these are so you can just kind of play around with different, if something is massless, so the energy and the momentum are are more or less the same, you can play around with which part has the most sensitivity. And you can kind of see below, let's say 20 GeV or something, it's tracking. And above, let's say 50 GeV, it's usually calorimetry. Atlas has very slightly different numbers and slightly different constants, but the form of the equations are more or less the same. There is a caveat because the Atlas collaboration uses something called topo clustering, which has dynamic suppression of noise. And so it's not exactly this. There is another, I think there is another term there, but it's basically comparable. But the numbers are comparable. The Atlas numbers are a little bit better for us than ours for their calorimeter. So I think their constant term error is, I think, 90% instead of 110, if I remember correctly, but I can't remember off the top of my head. Anyway, so that's basically an experimental aspect that you really need to do. There's a lot of ways to put this information together. And depending on what you want to do, you may, and it really kind of depends on what energy regime you're looking in and what you want to do with the information afterwards. We have some analyses that only want to use tracking. Those are called track jets. We have some analyses that only want to use calorimeters. They're usually, on CMS, they're called calorimeter jets, and on Atlas, they're topological cluster jets. Or you could put all the information together. At CMS, like I said, we have this thing called particle flow. And then there's a hadronic jet plus track event kind of thing as well. Atlas has also been using particle flow for a while too, but they have these topical clusters because they have an amazing calorimeter, which is the makes us green with envy. Because our hadronic calorimeter is kind of not great because we spent most of our money on the electromagnetic calorimeter and our tracker. For the next upgrade, where our forward calorimeter is going to be amazing because it's going to be made of mostly silicon, and we will be able to look at these showers in real time for the first time, which is going to be super, super, super cool. So what you do is there is no right answer here, right? You have a budget, you have to build things with actual steel and screws and wires and stuff. And so Atlas had up until now they have, I mean, even they chose to have the putting a ton of their resources into the hadronic calorimeter, and they use this topical clustering off their HCal mostly for their jets. And it's a really, really precise algorithm, and it's a really just impressive detector. It's super, super cool and does great resolution. CMS has a much better tracker than our calorimeter. Our hadronic calorimeter is a little dicey, but it does the job. And so we needed to use particle flow way earlier than Atlas because our hadronic calorimeter did not have good enough resolution. We had to add in the tracking in order to make it better. Okay. I have a couple of more minutes, so I want to go because you haven't seen this. I'll take a couple of extra minutes just to give you, just give you a couple of minutes. I do want to give you a couple of things that you may or you may not heard about. The most important thing for any experimentalist is pileup. Pileup will be the pain in your neck and in your rear and in your arm and in your back and your eye for the rest of your life. Okay, this is going to be, and it's getting worse. Okay. So protons are collided in bunches, right? So I told you each proton is a pancake. You have to put a lot of them together in order to make it intense enough to get collisions all the time, right? So what ends up happening is if you look at it at an interaction, this is the z-axis. So this is looking along the collisions like this. All of these yellow dots are different interactions in one bunch crossing. Okay, all the green are tracks that are happening outside of them. Which one is the correct one? I don't know. What we usually do is take all of the tracks, we associate them to the vertex, each individual vertex, because we can track where they went, and we take the sum, the one that has the highest sum PT. So you add everything together, and you take the one that's the most energetic, and that's the one we call the primary vertex. Okay. The good news is it's generally dispersed throughout the event. And so it's just kind of a dust or a cloud that's kind of floating through. And then your jets look like these collimated things. Luckily enough, this is also similar to underlying event. So pileup and underlying event are almost indistinguishable if you don't have tracking information. And even if you do, there is some underlying event. There is some pileup that will look like underlying event because you can't have 100% resolution there. So what ends up happening is the pileup and underlying event are spread uniformly throughout the detector, which is good for, and now you'll know why I told you that we want to use circular jets, right? Jets are collimated and if they're circular, they have a nice well-defined area. So all you have to do is take the median of all the energy that's in the rest of the event and subtract out the median area or the median PT per unit area times the area. And then you get the amount that should have gone into that little slice of your detector. Yay. So it's easy. It's a linear correction. And so this is the area of the jet, and this is the correction of the pileup in the KT algorithm. This is from Matteo and Gavin, and you can see it's very quite linear. And all you do, and this is for a single event, right? So you just linearly take out that correction, which is why you want circular jets. Okay. We also have we've gotten a little better in the last 15 or 20 years. You really want to use as much information as is humanly possible to remove pileup. So the way that this works is, suppose you have some interaction of interest and you make some reconstructed jet. Some amount of contamination will happen that you have something from your pileup interactions and they'll get into the jet too. What we can do easily is remove the charged particles from those interactions, from the secondary interactions. We track the particles back to here. We say, aha, it's different from over here. These are, a couple centimeters away. So we're going to turn these off and erase them. We're still left with the neutral particles. Okay. You can't do anything about them except, guess. You can guess. We use something at CMS that's called pileup per particle ID, or PUPI. We use, it's basically guilt by association. If your neutral particle is kind of close geometrically to a track that is associated to a secondary a non-leading primary vertex, you remove that particle too with some probability. There's a bunch of different algorithms to do this. There's self-killer and constituent subtraction and a bunch of other things that I'm not going to get into because I don't have time and I already ran out of my time. But anyway, this at the end of the day, this makes most of your tracks go away. Okay. I don't have a whole lot of time to talk about resolution of jets, but I think it's, if you give me 2 more minutes, I'll go through this as well. So you can investigate the resolution of jets experimentally to see how to do this. The resolution that I'm going to quote is the measured minus the expected over the expected. The expected can be there from theory, or it can be from some in situ calibration. There's a lot of factors that contribute here, right? There's the resolution of the individual elements of the detectors. If your calorimeter cell is this big, that's your resolution, that's roughly your resolution for your geometric space reconstruction, right? The efficiency and purity of your reconstruction algorithms will mean the difference between reconstructing a track and not reconstructing a track. If your track is not there, you lose resolution, right? You can also have natural fluctuations of neutral and charged particles. So I told you it's most of the time pions, and it's most of the time 2/3 charged and 1/3 neutral. That's not exactly always the case, right? That's only true on average. So there's fluctuations that you have to account for. That's just naturally occurring from the different radiation profiles in QCD. And they will also have some fraction of unobservable particles like neutrinos, or something that's just too soft to reconstruct. There's also resolution effects in the radius and the amount of pileup that's in the event. So wider jets have more pileup in them. Narrower jets have less pileup in them. So there's a whole lot of things that you have to worry about. This is just to give you an idea of the resolution as a function of the momentum. This is the angular resolution for our central region of our calorimeter and our forward region of our calorimeter for particle flow and calorimeter only jets in eta and phi. They're typically on the few percent level. As you get to very, very high PTs, it's a couple percent. So let's say 1 or 2% in your angular resolution. And in our forward region, it's about comparable. The numbers are about the same. So at low energies that you're looking at, it's around 5 to 10% at for calorimeter only jets. If you don't do any correction, the topo clusters are actually closer to particle flow than they are to our calor jets because our calorimeter kind of sucks. And so at low PT, you're looking at resolutions of let's say half of like 5% in angular resolution. The energy resolution is about 15% at low PT, and it goes up to about 5% at high PT. Similarly, one last thing I want to talk about is that the resolution of jets is a trade-off. That's important to remember, especially when you're doing PDF fits and all sorts of other things. The smaller the radius, the less perturbed. Jet that's smaller, you'll have some non-perturbative radiation. You might just miss some of it, and it's just going out of cone. Or if you have a larger jet radius, you catch it, but now you're more susceptible to pileup and underlying event problems. So this can be really a question of what, if you want, what effect you're actually trying to go for. And this will start motivating jet grooming, which if you have small jet radii, you'll have 2 jets for some events. Whereas if you increase the jet radius, it'll be 1. Going from this to this is jet substructure and jet grooming, which we'll talk about tomorrow. Okay, so I'm not going to talk about that. Just very briefly, all the stuff, there's a lot of little fun things on Gavin Salam's web page. The quality of jets is a great little app that will give you the resolution of, let's say, a dyed jet that, you know, that will go. You can pick the algorithm you want. It will change the resolution. You can adjust the amount of pileup that you have, whether or not you use subtraction to subtract out that pileup, whether you've got increased gluon fractions or quark fractions, different radii you can play around with as you go. You can have different, a bunch of different scales for Q, all sorts of different things. So you can play around with these and to see how it works as a little web applet. And I found it very instructive when I was a student to play around with this and a postdoc. It's great to get a feel for this. And it's kind of ballpark figures, right? This is a very old applet, and I think it's from ATV Collisions or something, but it's been, but you should still get the general gist. All right, so that's all I have for today. Is there any questions? Yes. That's correct. Which one? Yeah, the ECALs and HCAL, both the experiments, ECAL and HCAL is already pretty good coverage. I mean, it's almost down. I mean, if you actually look at these, they're like this big, right? We get to about this far, and it's, you know, from here to the door. The ADA coverage goes up to 5 or 5.5 or something without the tracker. So that's not really our problem. The problem is the tracking. So that's where most of the money's going. And it is a very expensive upgrade. So it's, yeah. Yes, very easily. So electrons versus charged pions is very, very good resolution difference. So electrons almost never make it to the hadronic calorimeter, whereas a charged pion almost always does. So yes, there is some, you know, inefficiency that can happen, but it's pretty high. I mean, the separation between electrons and charged hadrons is very high. No, that's actually very hard. Charged pions and charged kaons are extremely challenging to tell. Almost impossible. Not completely impossible. There are ways in with time of flight because they have different mass, and so they will travel at different speeds with the same energy. But that is, so we do have some timing improvements that are going to happen. And if I had a month to give you all this information, I could give you a whole talk on 4D tracking, which I won't. But there is 4D tracking will actually also help with pileup considerably, because the pileup is uniform in space and it also arrives at a specific time, so you can get rid of it. It's a lot easier to deal with it. But yeah, but kaons are one of the hardest things for jet resolution. If you look at these resolutions that I was telling you about, the strange content of quarks is really our limiting factor at very high energy. If we want to get this much lower than a few percent, we would actually need to do that. But that's the dominant factor. It's really, really hard. If you have any ideas, please come with them. Other questions? Yes. Sure. Yes. Yes. No. Jets, I'll talk about it. I'll talk about that extensively tomorrow. So jets are not massless. And that is because if you take these a particle and you radiate another particle, even if this is massless and this is massless, the combination is not massless. So I'll do that calculation tomorrow. There is an energy momentum conservation. I'm not in this diagram. There would be some recoil here. Any other questions? Yes.
I've heard sometimes we can also tag the work and proton.
Yes. That is a different process. So that's actually a soft process. That's when the protons are not destroyed. Most of the time our protons are destroyed, right? You have these pancakes that do this. Yeah, we do have some forward detectors. If you have a diffractive measurement where you have the proton that actually does not get destroyed. It's very challenging. It's not that high of efficiency, and you really kind of need low pileup in order to make it make sense. Pretty high. I think it goes, I mean, up to our tracking volume, really. It's up to, you can use the calorimeter to get even more forward, but the background becomes very high. But the rapidity coverage for us goes out to about 2.5. But yeah, you can tag protons. We do have some papers about that. Yes.
Really just a stupid question, but can we distinguish between glue initiated and port initiated jets?
Yes, and also no. If I have time, I'll talk about it. I'll talk about it tomorrow if I have time. I have a whole lecture about it. It is very challenging. The only difference between a quark and a gluon is that the quark line is, if you have a quark line here, it's just a color factor. So gluons tend to radiate more, so they tend to be broader and have more particles in them. That's the only real physics handle that you have. There is an amount, I could give you a month-long lecture. I mean, you could do a month-long lecture on just quark versus gluon. But that's the simplest answer. So yeah, yes, you kind of can, but it's really, really hard and it's not that easy. And it's not that good. Let's say we have about 60 or 70% purity. So that's almost the theoretical maximum. All right, any other questions? So I will be around tonight for your recitation / drinking hour. I don't know if you guys still drink on this thing, but we used to drink at these things, but I don't remember anymore. But I'll be around, so please come with questions.